Imagine a world where you could study and enjoy at the same time. But the moment someone looks at you, you can do only one thing. They look away and suddenly you are doing everything again. Sounds impossible, right? Well, electrons actually behave in a similar way. And this strange behavior is called superposition. To understand superposition, let's redo the famous double-slit experiment. Imagine you have an electron gun, a wall with two slits S1 and S2, and a detector screen that records where each electron lands. First, open only slit S1 and fire electrons one by one. And almost all of them land right behind S1. Now close S1 and open only slit S2. This time, the electrons land behind slit S2. But now, open both slits and fire the electrons one by one again. After some time, the screen lights up with a beautiful interference pattern, bright and dark bands, a pattern we usually see only with waves. Now let's zoom in on what makes this result so strange. Think about this single electron leaving the electron gun. We fire one electron and it is detected at a single precise point on the screen. But when we repeat this process many times and collect a large number of electrons, those individual detection points gradually build up a clear wave-like interference pattern. In the case of a single slit, electrons behave just like classic particles. But when we open two slits, they somehow seem to know that an interference pattern needs to form. How does a localized object released from a single point get information about the presence of two slits? The only way this can happen is if the electron spreads out in space like a wave. This makes it seem as though the electron behaves like a wave while it is traveling, but reveals itself as a particle the moment it is detected. According to quantum mechanics, an electron does not exist at one definite position. Instead, it exists as many possible positions at the same time, and its exact location is uncertain. We don't know exactly where the electron is, we only know the probability of finding it at different locations. This information is described by something called a wave function. At any given instant, the electron is associated with a wave that contains all the information about its possible positions. This wave function is not a physical wave made of matter. It's a mathematical wave that tells us where the electron could be and how likely it is to be found there. The probability of finding the electron at a particular position is given by the square of the wave function at that point. And since the electron must be found somewhere, all these probabilities together always add up to 1. In the case of double slit experiment, when both slits are open, the wave function of electron spreads through both slits. The two parts of the wave interfere, sometimes adding up, sometimes cancelling out. This creates the interference pattern. Before the electron hits the detector, its position is uncertain. It is spread out over many possibilities, and the probability of finding it any point is given by the square of the wave function. But the instant you measure it, the wave function collapses, and the electron appears at a single definite point. This is why you always detect a particle, but the pattern formed by many detections reveals the underlying wave behavior. So, what is an electron? A wave or a particle? In a way, it is a particle, but not a classical one. A particle whose behavior is guided by a wave. Now the question is, how can we use this strange behavior of electrons to perform computation? In classical computing, information is processed using bits, which can take only one of two values, 0 or 1. Quantum computing uses a similar idea, but instead of bits, it uses qubits. One common way to build a qubit is by using the spin of an electron. We label spin down as 0 and spin up as 1. Here is the key difference. In a classical computer, a bit must be either 0 or 1 at any moment. But in quantum computing, an electron's spin can exist in a superposition of both spin up and spin down at the same time. Because of this, the state of a qubit is described as a combination of these two possibilities. When we measure the qubit, it randomly collapses into one of the two states. The probability of measuring 0 is given by alpha square and the probability of measuring 1 is given by beta square. This is similar to how electrons behave in space, where probabilities come from the wave function. The difference is that a qubit is limited to only two possible outcomes, while an electron's position can have many possible outcomes. Now imagine a 2-qubit system. When we measure this system, there are 4 possible outcomes: 0, 0, 0, 1, 1, 0 and 1, 1. A general superposition of these states can be written in this form, where alpha square, beta square, gamma square and delta square represent the probabilities of measuring each of these outcomes respectively. Now let's apply a transformation to the system using a controlled NOT gate. This gate has two inputs, X, which is the control bit, and Y, which is the target bit. The outputs are P and Q. Let's apply the CNOT gate to each possible input state individually. A CNOT gate works in a very simple way. It flips the target bit whenever the control bit is high, as you can see here. From this behavior, we can notice something interesting. This transformation effectively performs the XOR operation, commonly used in classical computing. Now let's move to a more quantum mechanical situation. Suppose our 2-qubit system is in a superposition of all possible states, with different probabilities represented by bars of different heights that add up to 1. When this superposition is given as input to a CNOT gate, the output is also a superposition of multiple states. Now, if we carefully track how each output is produced, it becomes quite straightforward. The output state 0, 0 can only originate from the input 0, 0, so its probability at the output remains the same as it was at the input. Similarly, we can apply the same reasoning to all the other states, tracing each output back to the input state that generates it. Now, for this exact probability distribution at the input, a quantum state can look like this, or it can also look like this. Even though these two quantum states are different, the probability of measuring any particular outcome remains the same in both cases. We can also think of 2-qubit quantum states as vectors in a 4-dimensional space, where each possible basis state corresponds to one of the dimensions. In this framework, the quantum states psi1 and psi2 can be represented as vectors within this 4-dimensional space. Likewise, the CNOT operation can be expressed as a matrix in this space. By multiplying this matrix with an input state vector, we directly get the output state vector. Now I want you to feel the similarity between these two situations. In the first case, the wave function of an electron acts as an input. As it passes through the two slits, it evolves into a new wave function that displays an interference pattern. The two plots shown here represent the probability of finding the electron at different positions. In the second case, the input is a 2-qubit quantum state. When this state passes through a CNOT gate, its probability distribution is transformed across the possible basis states in a way that is closely analogous to how the electron's probability distribution changes in the double-slit experiment. In any method of computation, we always have a goal in mind. We start with a set of inputs and we ask what kind of system can transform those inputs into the result we want. Take the example of the double-slit experiment. If you want to change the interference pattern of an electron, you might move the screen closer or farther away, or adjust the distance between the slits. Each change gives you a different pattern. But in this approach, you are essentially experimenting by trial and error, adjusting parameters and observing what happens. Now imagine, instead of that, you already have a mathematical equation that tells you exactly how a system transforms its inputs. With that knowledge, you can deliberately design a system to produce a desired outcome. This is exactly how classical mechanics work. When we throw a ball with certain initial velocity and acceleration, we can use the equations of motion to predict its velocity and position at any later time. In quantum mechanics, we have a similar guiding principle, the Schrödinger's equation. This equation tells us how a given wave function evolves when it passes through a physical system. Using Schrödinger's equation, we can predict what will happen if we use 3 slits instead of 2, without relying purely on trial and error. In the same way, Schrödinger's equation also determines how quantum states transform when they passes through quantum gates, allowing us to design and understand quantum circuits systematically. Now the solutions of Schrödinger's equation reveal some important limitations on how quantum systems can be transformed. One key result is that a closed quantum system can never lose information. But what does that actually mean? Consider a quantum state that is transformed using a CNOT gate. In this case, from the output state, it is possible to recover the original input state by applying an appropriate quantum operation. In fact, for this one, applying the same CNOT gate again brings the system back to its initial state. Now compare this with a different kind of transformation, such as applying an AND gate to both inputs. Here, multiple input states like 0, 0, 0, 1 and 1, 0 all lead to the same output. Once this happens, there is no way to reconstruct the original quantum state because the information about those distinct inputs has been permanently lost. This is why quantum gates only allow reversible, probability preserving transformations on quantum states. Any operation that destroys information cannot be a valid operation in a closed quantum system. But what about the measurement of qubits? Measurement is not reversible. So does that mean quantum systems sometimes follow Schrödinger's equation and sometimes they don't? It turns out that only closed quantum systems evolve according to Schrödinger's equation. In other words, if a system is evolving according to Schrödinger's equation, it must be a closed quantum system. To understand what we mean by a closed quantum system, let's look at a simple two-state system. Suppose the initial quantum state is like this. If we apply a poly-Z operation, which is a reversible and probability preserving transformation, the state changes smoothly. The same is true if we apply a poly-X operation. The system continues to evolve according to Schrödinger's equation. However, the moment we measure the quantum state, we inevitably disturb the system. The wave function collapses and the system is no longer closed. From that point on, its behavior can no longer be described by Schrödinger's equation. So, as long as the quantum system does not lose any information, it remains closed and follows Schrödinger's equation. The moment we interact with it through measurement, the system is disturbed and the wave function collapses to a single state. Now, how can we use these quantum computing principles to solve a real-world problem? Let's take the example of a Sudoku puzzle. Consider a Sudoku grid with 50 empty cells, where each cell can contain any digit from 1 to 9. If we represent each digit using 4 qubits, we would need a total of 200 qubits to describe a solution of this puzzle. Now imagine these 200 qubits together. This system can exist in a superposition of 2 raised to power 200 states simultaneously. And let's start with a quantum state in which the probability of measuring any one of these solutions is equal. To determine which of these states represents the correct Sudoku solution, we can design a verifier circuit. It checks effectively in parallel whether each possible input satisfies the rules of Sudoku. This verifier takes the input qubits and using a sequence of quantum gates forms a closed quantum system. At the output of this verifier, we obtain a 1 if the input corresponds to a valid solution and 0 otherwise. The challenge is that the input itself is a superposition of all possible solutions. So the output is also a superposition of all those states, except that the correct solution is now marked by the verifier. At this point, if we try to identify the correct solution by directly measuring the verifier's output, the probability of finding it is still 1 divided by 2 raised to power 200. In practice, this is essentially impossible. You can imagine this situation like this. This closed quantum system knows the solution, and now we need to somehow do something so that it can reveal the correct answer to us. For that purpose, we use something called Grover's algorithm. Initially, all possible solutions of the puzzle have equal probability of being measured. Using Grover's algorithm, we iteratively transform this probability distribution so that in the end, the probability of measuring the correct solution becomes very close to 1. Let's understand Grover's algorithm by looking at a 3-state quantum system. You can imagine the wave function here as a vector in a 3-dimensional space. For example, if we start with a quantum state where each state has equal probability, it will look like this. Let's assume that out of these 3 states, the third state gives a 1 when passed through the verifier. So essentially, we want to transform our quantum state from this to this one. In Grover's algorithm, we design the verifier such that when the input quantum state is passed through it, the correct solution is marked by flipping its sign. This output quantum state of the verifier will look like this in the 3-dimensional system. Now visualize that these 3 states marked in red all lie in the same plane. Let's look at these vectors within that plane. Here, psi is our input quantum state where all solutions have equal probability, and psi dash is the state where the amplitude of correct solution is marked by flipping its sign. To transform psi dash so that the probability of measuring the correct solution increases, we do something clever. We take the reflection of psi dash with respect to psi. This results in a new quantum state where the probability of measuring the correct solution is higher than for the other 2 states. Notice that we have applied 2 types of transformations here, marking the correct solution using the verifier and reflecting this marked state with respect to the initial vector. Throughout these transformations, only the verifier knows which state is correct. Even if the verifier had marked some other state, reflecting that quantum state would increase the probability for whichever state the verifier marked. Importantly, all these operations happen in a closed quantum system. We don't know which state is marked and we cannot perform any measurements here. We only know that the probability of the correct solution increases after these reversible and probability preserving operations. This process can be repeated. We pass psi double dash to the verifier. The sign of the correct solution is flipped again to produce psi triple dash, and then we reflect it with respect to the initial equal probability state. This further increases the probability of measuring the correct solution. Now let's look at how this works mathematically. We start with a quantum state where all solutions are equally probable. First, we apply the verifier, which flips the sign of the correct solution. Next, we apply a reflection matrix, which increases the probability of the correct solution. After this single Grover iteration, the probability of measuring the correct solution becomes 92.6%. By applying these same transformations to the quantum state representing a Sudoku puzzle, we can know which state is marked by the verifier, which will be the solution of our puzzle.